In the Sunday morning. That's yeah, right.
We are going to start. It's our last day. I saw the luggage there. It's breaking my heart, but yeah, we like to have you here. I hope you come back very soon. Then this is the last day today. I still want to remind the code of conduct that really matter to us, and you can read more about this and report any ethic concern on the link over there. Something that people ask me, yesterday 2 people reached in the survey. They have heard a lot of coughing, and I noticed also yesterday that it was starting to be a lot of coughing. Please, if you are coughing and sneezing, and we would like to encourage you to put a mask that we have outside. It will make feel other people more comfortable. Thank you. Then also, I'm going to remind you this. You had a survey previous day, and I see that every day I get less reply. It's expected. It's not too late to reply to the one you didn't fill yet. And then also you will get a big survey at the end of the day today. We will have a little bit of time together to fill it. But I'm saying this, dear, because some of you might be already in the bus to the airport. Then please fill the survey. It matters to us. It helps us to improve our material for next year. Then it means if you fill the survey, you are technically part of the next CSM tutorial because your feedback is included. I take really all feedback. I read every remark, every comment, and I take it very seriously. Then also, some people, I'm going to add a slide in Dave's presentation this afternoon, but I wanted to put this up because some people ask me, and I'm afraid the one that are in the bus will not see it. Then people wonder how long they will keep the account. I was told by CESM that you will have the account active until August 31. I have no control on this. It's what they told me, but I think it's accurate information. But when the computer time, sorry, I missed the word time. When the computer time is gone, you will run in the situation that we had the other day. It will not, but I cannot say, oh, I want more computer time, like we had on Wednesday. That please don't use this for your own simulation. If people want still to do some exercise, you can use it, but don't run your own project simulation for your PhD on this. It's little, and we would like it to keep for this group of students to do the exercise of this tutorial. And also, how can you get an allocation on the ratio? Then there are some information here. You can have small allocation for researcher at US institution, and I'm sorry we cannot give allocation to international people, but I think they can get sometimes an account if, let me finish, yeah. They can get sometimes an account, go with the mic there. They can get an account, because I'm talking and I had to the mic at the same time. They can get sometimes an account, it's him with the mask here, yeah. They can get an account, sometimes being a collaborator. I don't know exactly the rule of CESR. I'm not making them, but reach to us if you have question about this. Yes?
Oh, just wondering if the tutorial queue will be active through August 31st.
It's what, oh no, the tutorial queue, it will be finished today at 5:30. Yeah, it's a good question. Don't use the tutorial queue at 5:30 today, you become a regular citizen like all the rest of us. You have no privilege anymore. You have to wait in the queue like everybody else. It was just we were giving the tutorial queue because you have 2 hours to do your exercise, and if the machine is busy, then it's a good question. No, don't use the minus Q. It's outside of the lab. After today, I think even today I'm not even sure if it's 5:30. It might be even earlier today because we have no lab this afternoon. The tutorial queue will go away. And it will be clear. It will reject when you submit the job. OK, then any question on this?
I just want to add one thing. So next week, Richard's down.
Yeah, talk in the microphone. Yeah, then also the ratio is going to be down next week. Then when you will try to connect, I don't know exactly the date, but yeah, the machine might be down. I can figure out and put the time of the ratio downtime later today. I will add this to the slide.
The date is 12th through 15th.
OK. OK. Okay, then thank you. If there is no question, we're going to move to the next talk. And this is a talk I like to give people a little bit of behind the scene of how we built a climate model. You have been running the model for a week. You have been meeting a lot of scientists, either in the lab or gave talk over here who are building the model. But I want to give you a little bit of information how it's done in practice. And what I'm going to cover, then the timeline, when we built the version you are using now, it's already an old model. We will have a release in the next year or so. The timeline, how we build this model. And then I will talk about the art of tuning, and I will give you some tale of coupling. Then, this is how we built CSM2. When we built CSM2, then for 5 years, we developed individual components, the atmosphere, the land, the sea ice, everybody working in his own little group. The effort for CSM2 started around 2010, and it was a while ago. And then individual component was really we talked to each other, we like each other, we talked to each other at the cafeteria, but we were not really working much together. Then for 5 years, we built a different component. And for example, for the atmosphere, we developed new dynamical core. We work on new resolution. We did new physical parametrization. And we do a lot of many uncoupled simulation for the atmosphere, the F-case like you were doing yesterday for the people who were in the atmosphere exercise. But we do a lot of simulation of that component. And the other working group were doing something similar. Then after, when we were happy with the component, it's not moving. Okay. Then after we put all the components together, then it means all our teams start to work together to really assemble the model. It was a lot of meeting with everybody. It's all the working group co-chair and liaison. We had like hundreds of configuration that we try, we test. We look at thousands of years of simulation and diagnostic. And at the end, we released the model in June 2018. Then it was the timeline. And basically, this is our timeline. We started in 2010 and we finished in 2018, and along the way, there were a lot of tuning and coupling. And I'm going to explain a little bit what are these that we use along the model development. Then first, the art of tuning. And tuning, it's basically adjusting parameter, what we call tuning knobs, to achieve the best agreement with observation. And here the word, for now, it's adjusting parameter. What are the parameters that we adjust? Then it's basically parameter weakly constrained by observation. I'm not going to tune gravity, or I know the number, but there are some parameters that exist only in the model, that some parameters don't even exist in the reality, and it's the parameter that we are using. And an example that we use, it's DCS. It's the threshold parameter to convert cloud ice particle to snow. And I'm going to explain a little bit what is this. Then you have the cirrus cloud. It's the cloud very high in the atmosphere, and they are basically made of ice crystal. It's what we call the cloud ice. And they are in high latitude, above 5 kilometers. A few here behind Ankara is in the little corner over there. Then, basically, we can represent a cloud ice, a cirrus cloud in the model, like composed of different particles of different size. There are bigger one and smaller one. And what we know, if you have bigger ice particles, they're going to fall out of the cloud. It's when we say the cloud ice convert to snow. And basically, we can decide on a diameter. You say, if these particles are bigger than this, they will fall out of the cloud. And it's basically what DCS is about. But in reality, it's not first particles are not circular. They don't have a diameter. Then it's much more complicated than this. But we can have a tuning knob to tune the model. What's going to be the impact of the model? Then if you have smaller DCS, you will have more particles that are going to fall out of the cloud. It's a picture on my site. And if you have large DCS, you will have more cloud ice. And what's going to be the impact on climate about this? Then basically, if you have more cloud ice, you will have less infrared radiation going back to space. Then this is the way that we adjust some parameter. And the other thing is to do agreement with observation. Then how do we look at the DCS? Then basically here you have the Earth radiation budget. And DCS, basically this is in the infrared radiation, in the infrared radiation over here that you are tuning this parameter. Then why is it important that we tune the atmospheric radiative imbalance? And this is because that if you don't use the balance, this is an example of a simulation. I had a radiative imbalance that was positive, then I have more energy coming in my system in this case than energy getting out of my system. Then basically all the heat will go in the ocean. The atmosphere has a very low heat capacity, then all the heat will go in the ocean, and you will see that the temperature of the ocean is going to increase slowly. Yeah, then the top of the atmosphere needs to be near zero. And as a target, this is an example. We look also a lot at the cloud forcing, then the shortwave cloud forcing, the longwave cloud forcing. We look at precipitation, answer amplitude, the AMOC, the CR thickness, and extent. And it's a lot of things that we look when we are tuning the model. Then there are a lot of dilemma also when we are tuning. Then there are the subjectivity of tuning target. You cannot have everything right. Usually it always involves choice and compromise. Sometimes if you get the precipitation better, it will be to the detriment of something else. But the good thing is that overall tuning has a limited effect on the model scale. Also, do you want to tune to pre-industrial, where you have radiative equilibrium, like the PI control that we were doing, the B1850 that you were doing in the lab? Or do you want to do present day, where you have available observation, but then you don't have the radiative imbalance, and some modeling center do it other way. What we do here is to tune pre-industrial. Then also, do you want to tune the individual component on the couple model? Then tuning the individual component, it goes very fast. You can do a lot of simulation very quick, but there is no guarantee that the result you get when you tune the model in an individual component. For example, if I tune the atmosphere, will transfer when we do this in the couple run. And I'm going to show example next. And then the good news is that all this tuning is very educative. Then you learn a lot about the model when you are doing the tuning phase. Then now the art of coupling, or some tale of coupling, that I want to show you a few examples when we start to put all this model together and we start to run the couple model, what can happen. And I like to say that coupling, it's unleashing the beast. For example, when I do my EMIP type run, an EMIP type run, it's basically when I run only the atmosphere and I prescribe SST, and the model is really well behaved when you do this because you prescribe the SST, even if you have a top of the atmosphere radiative imbalance, you prescribe the SST, nothing will happen. But then once you put a full ocean model under it, you can have couple bias and you can have feedback and you can have very quickly a running away simulation. And I'm going to give a few examples of this. Then one of an example, it's already older, but I like this example because we did all our tuning. We were tuning CAM5. The version you have, it's CAM6 now in the model, but we were tuning CAM5. And we did everything in EMIP mode, then the standalone simulation, and we were so proud of ourselves. We had a perfect simulation. Then we put all our tuning into the couple model, and within 12 years, the model, you had like very cold SST bias that happened in the North Pacific, and it went really quickly. 12 years, it's very quick in model time. Then what was happening, we had colder SST over there. Then because the SST were colder, we had more clouds that were created in the North Pacific, and then it was even cooling the SST, and then you had the sea ice that start growing, and then because it was growing, we had even colder SST, and we had a running simulation in absolutely no time. In 12 years, it was out of control. Then even that we had this perfect simulation with the atmosphere only, we had to make it less perfect that it works in couple mode. Another example that I have here, it's when we try to change the spectral element decor, when we went from finite volume to spectral element. And the spectral element will be the default resolution in the CSM3. Then basically, when we did this, you would think that a decor should not have much impact on the simulation, but indeed it did. Then in the CAM standalone, the finite volume and spectral element decor were really producing very similar simulation. You will run with one decor or the other. It was almost boring. It was the same. I could not even tell which one was running. But then when we put this in couple mode, suddenly with the spectral element decor, we had a drop of the sea surface temperature of half a degree within like 30 years or so. And we spent a lot of time figuring out where it was coming from. And basically, it was coming from the zonal surface stress. If you look on the plot on the right, the black light, it was the finite volume. And then when we put the spectral element decor, it moved a little bit north. And it was this very slight difference, but it was at a very crucial point where you have the atmospheric circulation that's very important that was responsible of this cooling of SST. Then we knew where it was coming from, but we didn't have an easy way to fix this. And at the end, we delayed the release of the spectral element decor as a default. Then it's another example of what I call unleashing the beast. The last example that I want to give, and we are dealing with some of the issue again in CSM3, is the Labrador Sea. The Labrador Sea is really a complicated problem. Then on the left side, you have a thin black line that shows the sea ice extent. I don't know if you see, I'm not going to touch the screen, but there is a thin black line over here, and it shows the sea ice extent. And the Labrador Sea, it's the black box on the other side. Then you see in observation, CSM1 was really doing a fairly good job with the Labrador Sea. In CSM2, we had in some simulation, the sea ice will grow in the Labrador Sea, and sometimes it happened after 1 year, 40 years, or sometimes even 100 years. And it was a very tricky situation, and it's why it took us 3 years to. It was one of the reasons it took us 3 years when we start to do the coupling to be able to release the model. And we are dealing with some of the same issue right now in CSM3. And basically, we understood in CSM2 what was happening, why it was freezing. We had error in CSM1 and we had error in CSM2. CSM1 was too warm and too salty. And CSM2 was too cold and too fresh. The amplitude of the error was about the same, but in different direction. But in CSM1, too warm and too salty was helping us not to have the Labrador Sea growing, while too cold and too fresh was making the Labrador Sea easier to freeze. Then it was the reason. Okay, then I hope I convince you in this very quick presentation that when you are doing really all the coupling, you are unleashing the beast and you can have really runaway simulation. And then one of the things that we have been doing, I say in CSM1, we did like, let's build a component. We worked 5 years together, and then we did the finish. We did, let's couple all the components together. And this time we are not doing as straight as this. We are doing like a loop. We come back, we couple, and then we work again on the component, and we couple, and we come back, not to have a big surprise at the end. Okay, then this is the summary. Then the art of tuning, it's adjusting parameter, what we call the tuning knob, that are weakly constrained by observation and to have the best agreement with observation. It involves choice and compromise, but we learn along the way a lot about the model. And then I show 3 examples of things that can happen when you are doing coupling. And then, yeah, this is it. If you have any question, we have 5 minutes. No, we have 15 minutes. Yeah, and this is, here, before I was showing Minecraft, it was my son. This is my husband. Then I go and I will ask my husband, can you do a little cartoon? My husband is a space physicist. He works on Jupiter, but he likes to draw. And I will ask, can you do this or can you do this? And then
I was going to ask you.
Yeah, it's not, I don't find the perfect stuff online. I order them, but it's...
The cartoon is very cute.
Yeah.
My initial question was like, who draw that? So
Yeah.
I think of another question. Like, what's the methodology used in the tuning process? Perturbation parameter or any other optimization method?
Yeah, then there are different processes. A lot of what we do still right now when we do this tuning, sorry, I'm going to do a faster way. A lot of things it's to look at single simulation. We do a simulation, we look at a simulation that's long enough, and it's really human experts that are looking at parameter. We have different effort. For example, we have the PPE, and I see Peter is involved inside this, and he can probably see a little bit more when we are testing a lot of tuning parameter. But usually when we run the model, my presentation disappeared, but when we run the model, we don't use like tons of tuning. There are a lot of parameters that we could tune in the model, but I would say that we use most of the time in the atmosphere maybe 10, and when we realize we are stuck with this, we will use another one. It's even less. We have a small pool of tuning parameters that we use to adjust the top of the atmosphere in balance. Then we have now effort like the PPE, where we do a lot of simulation when we look really at the space of the tuning parameter to try to see the impact of this tuning parameter. And I don't know, Peter, if you can say something about it more, because I was not involved in this effort. But most of the time, they're going to bring the mic to Peter, but most of the time, the tuning right now, we do it without doing a lot of ensemble. We adjust it. We have a lot of experience with the tuning parameter, and then we do a simulation. We tune it. We change the parameter a little bit, and we look at a bunch of diagnostic to see the difference, the impact of this tuning parameter, to see if it goes in the direction we want, if we can adjust the atmosphere radiative imbalance without screwing up something else like the precipitation, and then we move to the next step. Peter, yeah.
Sure, just to put things a little bit in context, what Cecile is talking about is like people having decades of experience with the model kind of know which knobs to turn. And I think the PP, perturbed parameter ensemble, is an attempt of doing that more systematically. So you provide a list of parameters and a range, and then you run a bunch of simulations so you have a large enough ensemble to kind of populate the space, and then you can do all kinds of fancy stuff to understand the results. The obstacle with the PP is you need, hundreds and hundreds of years of simulation. So the current PPEs we've been running, we only run the model for 2 or 3 years, and then do all the analysis based on that. And it's done in F case as well. And the variables that are being looked at are in general just global means of like shortwave cloud forcing or precipitation or U200 deviations from observations, et cetera, et cetera. So while that is useful, it also has big limitations. For example, if you only run 2 years, you're not getting the polar climates correct. You need minimum 10 years to look at that. So it's really hard to look at things like that. But it's very useful to look at tropical circulations because they set up really, really fast. So I've had conversation with people about the PPE here, but I really think we need more diagnostics to look at. So for example, the water vapor tape recorder, for example, can get completely messed up with some tunings that you won't see in the PPE because we don't look at that in the PPE, for example. But the greatest challenge, I think, is what Cecile said, is when you go from F case to B case, so from prescribed SSTs to fully coupled. I wish we could do a PPE fully coupled. Only problem is you need to run a very expensive model for 100 years or so because it takes a lot longer to spin that system up. So there's really pros and cons here.
Yeah, but the point is right now we are still doing a lot of things with expertise that has been acquired of many, many years and looking at a lot of simulation. And there were other efforts to try to automate the tuning, but so far it's what still works the best as now it's to have expert of the simulation looking at the run. And we have a group of people, we have a large group of people that are looking. We are working really as a team. We meet as all the people of CSM, we meet once a week on Tuesday, and we talk together. And the atmosphere meet also every week on Friday. Today it's canceled because usually we meet at 10. But we meet once a week in our small group, and then once a week with the large group, and the other component do the same. I don't know the frequency of the other component meeting, but I think it's also once a week or once every 2 weeks. And sometimes we even need to meet, I don't know, it seems we are all the time in each other's office, we are all the time talking together, then there are a lot, it's really a teamwork. It's not a one-person effort, it's a teamwork. And then we run the simulation. I'm doing a lot of the simulation, but I'm not the one who look at it. It's just I run the simulation, I do some diagnostic, and then a team of people look at this and assess them and decide what are the next steps. And then we meet together and we decide and we disagree, but we discuss. And then it's a very fun, sometimes it's very frustrating. The Labrador Sea, for example, has been a nightmare sometimes, because it can freeze. The simulation goes well, and then after 100 years, it freezes. And in this configuration, we don't know. It's that we are just borderline of freezing, and once this happens, it never. What we know, it's once it's frozen, it never come back. But we can never predict. We have tried to see precursor of what was happening, and we have not been able. Between CSM1 and CSM2, I was showing that it was really clear that it was because we had CSM1 too warm and too salty, and CSM2 too cold and too fresh, but we are still in a configuration too cold and too fresh, but some simulation freeze and some don't, and sometimes it's not really easy to understand why. Other question? Yeah, Greta. Oh, and there is one here. You can give and then come. Yes?
I'm just curious because you said that like some parameterizations run better uncoupled and some run better coupled. Have you ever released like different parameterizations for those two setups, or do you always kind of go with what runs best in the coupled model?
Yeah, no, we don't do, it's not the parameterization, it's parameter from the parameterization, then it's what I was like showing, the DCS, and we use the same parameter in couple and in standalone. But then sometimes we use, sorry, I make you sick here. Yeah, this is an example of a parameter that we tune, DCS. We were especially using this in CSM2. We don't use a different value in standalone and in couple, at least for the atmosphere. But then we use sometimes different parameters at different resolution. Because when you have different vertical or horizontal resolution, it can change this kind of, not for the DCS, but for some other parameter, the resolution will have some impact. And then you will have also different parameter. For example, with the current version of the model, we are developing CAM7, then the version 7 for the atmosphere model, but you can still run CAM6 and you can still run CAM5. And sometimes this different version of the model will have different version of the parameter, but it's because it was tuned as a whole for that version of the model. And then if you have another version of the model, you have another set of parameters. Then different version of the model, different tuning, different resolution, different tuning, but we don't do different tuning between standalone and couple. Yeah.
Are there any specific things you do to prevent compensating errors? Like how do you know that what you're tuning is the actual problem and not something else?
Yeah, then often we have compensating, it's really like what was happening with the Labrador Sea. Sometimes we have error that help us, and then you can have, sometimes you get the right answer for the wrong reason because you have compensating error, and we know that sometimes they're compensating error because we compare to observation and we see that there is an error, but there is, sometimes then we have to try to figure out how to add some more physical, some more process in the model to make it more realistic and more physical. Because we always try to have the model to do the right thing, but the more stuff you add in the model, the more complicated it becomes, and sometimes it's, yeah. Sometimes better physics doesn't make it a model that's going to give a better simulation, at least right away. Yeah.
Thank you. Yeah. I just wonder what's the role of resolution in the development and how expensive it could be to try maybe to go further into finer resolution. Do you even attempt to go to the finer resolution to compare if that is the sole thing that's kind of a major difference, or you just fix the resolution that's, yes, we want to go for 1 degree horizontal and let's do the development for this?
Yeah, then really what determines our resolution, there is like what we want to look at, but there is also the computer power that we have. Then it's the size of our supercomputer. We might love to run like simulation at very high resolution, but then it's harder. The 1 degree resolution, it's in part determined, but because we want to have enough ensemble, we want to be able to look at variability, and it's why we have some resolution. But there are some phenomena. For example, if you want to look at hurricane, a 1 degree resolution doesn't help you. You cannot look at hurricane. Then for this, we will have we will run at 1/4 degree, and then we will have, right now we have even some scientists that are running 1/8 degree resolution, and Adam will give the next talk. We are also having version of the model where you have variable resolution in different parts of the model. And yeah, then I don't know if I answer your question, but.
Yeah, I just wanted to know, how do we make a decision because of the computational expensive things, to go for this resolution for development of this version of the model. So yeah.
Because if you want to run the model, it's what we can afford. If you want to, we know that we need to run the model like the pre-industrial control for 500 years or for 1,000 years, and then we want to do a number of ensemble, but it's a little bit what determine the resolution that we are going to use. And also there are resolutions that don't really make sense to go. For example, if you're at 1 degree, to go to 1/2 degree, it will bring you very little in terms of new things that you can learn. Then you should go to 1/4 degree, because if you go from 1 degree to half degree. There are a few half degree simulation, but usually you cannot see still the hurricane. Then what really determines it's what you want to look at and also what you can afford. It's like when you buy a car. It's not what you would like. It's what you can afford.
Thanks.
Then yeah.
Thanks for
and
the.
I think it will be the last question. I will be there. I'm always there. I will be there after. Then I'm happy to talk with you, but I don't want to talk anytime on Adam. That's going to. Can we all, because it's 9, then I don't want to take any time from Adam. Yeah. Okay. Thank you. And I will be here.
Just in the nick of time.
Yeah. No, it's you. You're at 9.
Oh, okay. Okay.
Yeah.
Okay. Hello.
There is like this, and nobody is able to make it work.
Okay.
But a few are.
Is this too loud? Am I coming off too strong here, guys?
No, it's good.
Okay. Okay, so I'm Adam Harrington. I'm a project scientist here. I am a CAM developer, work on all things CAM. From supporting the model to bringing in new functionality, whether it's physics or different grids. Yeah, that's what I do. So I'm going to talk about variable resolution CESM. And so we'll start the talk with, what is VRCSM, why use it, and how do we use it. So variable resolution is, swap this real quick. Oh. Yeah, I messed up, Cecile.
Yeah, no, it's fine. Sometimes it does funny things.
I swapped it manually thinking that I could get the presenters mode on.
Back there was a slide. There was a button swap display.
Let's try again.
And on the top.
Yeah, I don't know how to get your mouse over there.
Oh, okay.
Oh. Yeah, then it went in presenter mode. Oh, okay.
Is there any way to see the full screen on the computer too?
Yeah, no.
Okay, I'll just look. All right. So variable resolution is CSM's term for static mesh refinement in CAM. And so static mesh refinement is just one type of grid refinement. And so another type is called domain nesting. So domain nesting is when you take a limited area model, all right? So it's a high resolution limited area model, and you insert it inside of another model, a bigger global model. And that provides regional refinement over that limited area where you've placed that model. And so it will interact with the host model, and so you have two models running simultaneously. Static mesh refinement, which is what we do in CSM, is where you refine a region of the grid in the same model. So these meshes up here I developed for CAM, and as you can see, I'm just sort of refining regions of the planet, over the Arctic, over the North Atlantic. And then the sort of holy grail of mesh refinement is called adaptive mesh refinement. And that's where you're actually refining, it's the same as static mesh refinement, that you're refining the grid in the same model, but that where you're refining is dynamic in time. So you may want to refine certain regions where a cyclone is developing at a particular time, and other regions that are quiescent you don't want to refine. So there's no operational atmosphere model that that has adaptive mesh refinement, but there's an operational ice sheet model called Bicycles, developed by Dan Martin at Lawrence Berkeley, and he has some nice visualizations that I figured we could try to show you, but I don't know how to do it. Hold on one second. We'll just do it this way. Work with what you got. So this is a visualization of the Antarctic ice sheet undergoing a West Antarctic ice sheet collapse. And the colors are the resolution of the grid. And so around the grounding line, you have the black colors of the highest resolution. And in the interiors, you don't really have, you have lower resolution. And you want to throw higher resolution at the grounding line because that's where the ice sheet actually lifts up off its bed, becomes buoyant because it's starting to go into the water, into the sea, and that changes the force balance fundamentally on the glacier. And so you need to throw more resolution at that to refine it properly. So under this retreat scenario, you can see the West Antarctica is collapsing due to the marine ice sheet instability. And as it retreats, you start retreating where you're resolving the ground. So let's try to see what this looks like and with a more sensible field. This is just ice velocity and ice thicknesses in the rasters. And so you can get a nice simulation of the dynamics of the marine ice sheet instability. If you look at the time axes here, it's taking a few hundred years to collapse the entire West Antarctic ice sheet. So what we do in CAM is static mesh refinement, and I have a visualization for that too. So this is just the 1 degree CAM model, or it looks like it's your 1 degree CAM model. This is the total precipitable water field. But you can see that we're actually the grid here, and we're refining this region over the Arctic and Greenland to the 1/8 degree. And it'll start to show some storms developing. So this is a precipitation rate and the wind speeds. And you can see as these storms sort of penetrate the refinement region, they do so seamlessly, and they start to dump precipitation on Greenland. This is looking a little closer to zooming in on Greenland, looking at the lowest model winds. You can resolve some katabatic winds in this grid. And you can also compute the surface mass balance because the CSM is coupled to the ice sheet model. And so this is what the instantaneous surface mass balance looks like over the course of a few months. Snowstorms are dumping snow on there and accumulating ice. And then during the summer, you'll see the ablation regions of the melting crawling up the sides of the margin and then going back down once we get into the fall. All righty. Let me get back to my presentation here. Okay, so why do we do variable resolution CSM? The appeal is because we can simulate high resolution on a global model, but at an affordable cost. You can make the impossible possible in some sense. So what we're showing here is just the wall clock time or the execution time of the model in the blue bars is a global 1/4 degree model. And in the pink is the variable resolution where we're refining a portion of the model to 1/4 degree and the rest of it is 1 degree. And so it's about 1/5 of the execution time. And that's also shown over here where the global 1/4 degree model is about 100,000 core hours per simulated year, whereas this Arctic grid down here does quarter degree just over the Arctic, and it's about 20,000, so about a fifth the cost. And so what the models that support variable resolution in CSM are the 2 atmospheric dicores that we have based on unstructured grids. Peter had probably gave you a little taste of these dicores on Monday, though he spent most of his time talking about the finite volume dicore, which this is not. So the MPAS-A dynamical core was developed at N-Cubed, the lab down the hill. Only very recently have we ported this thing into CSM 2.3, which is exciting because it's a non-hydrostatic model, so we can run it faithfully at scales from 3 kilometers down to hundreds of meters, and the equations are valid. And so this is a dicore primarily for mesoscale applications. It's based on the centroidal Voronoi meshes, which is basically just the sphere is just populated by hexagons. It's populated by these hexagons, and you discretize the equations of motions on these hexagons, so you get like the winds are at the center of the faces, actually, and so you get winds in all sorts of weird directions on this grid, which is that's a property of unstructured grids. And so it supports refinement. As you can see, you can have a gradual mesh transition, as shown there. The other dicore is the spectral element dynamical core. This was jointly developed by NCAR here and Department of Energy. It's hydrostatic, and so you can run it down to about 7-kilometer resolution, but anything else is invalid, and you won't get past the review process if you submit a paper with a hydrostatic model running below 7 kilometers. You'll probably have trouble getting past the reviews even running a hydrostatic model at 7 kilometers, because it's not everybody agrees that you can run hydrostatic models 7 kilometers. 10 kilometers seems to be the magic number, so if you're 10.01, you're good. If you're 9.99, you're not good. So those are the challenges of reviewing, getting these types of papers published. It's based on a cube sphere mesh. If you don't know what that is, it's a cube, so a cube is 6-sided, and you blow it up, you inflate it to the size of a ball. So it looks like an inflated cube, and then you divide up those cubes into these elements, these quadrilateral elements, and then the actual, these are finite elements, and so there's actually 16 nodes inside an element that provide you our grid points, basically. And so these are 3 meshes down here that run out of the box in CSM 2.3, which is our latest code bases. And so anybody can run these spectral element variable resolution grids, and there's instructions for running them at the user's guide for Camp 6.4 there. Okay, so what dynamically do we need to change in the model? Or how do we need to configure the model differently in variable resolution? It's easy to answer the question of what do you have to do to a model when you increase horizontal resolution in general? So one thing is that you need to reduce the strength of your numerical filters. So GCMs, or atmospheric dynamical cores, I should say, the grid scale solutions, so 2dx, where dx is the grid spacing, those modes are not accurate in dynamical cores, and so we have explicit numerical filters that filter out any small 2dx modes trying to gain traction in our dicore. But at higher resolution, you can relax those because you can support finer scale features, and so you do need to reduce your explicit numerical filters at higher resolution. VRCSM uses a scale-aware tensor hyperviscosity in which basically the amount of filtering is proportional to the local element size. And so it does this sort of in a scale-aware way. You also need to reduce your time steps. In the dynamical core, you need to do this for stability. It's an explicitly time-stepped model, and so it does have a CFL criterion. You also want to do that in the physics as well, and that's less for stability and more for physical realism. You want to keep the dicore and the physics sort of interacting at the same time scales. And the final one is you increase the resolution of your boundary conditions. An example of this is topography. So when you're preparing a topography data set for a GCM, you want to smooth out all those small grid scale features. So 2DX type length scales in the terrain data set, because the last thing you want to do is sort of excite or generate these inaccurate modes in the die core. And so we smooth away all of the grid scale features in the topography data set before we give it to the GCM. So at higher resolution, you need to smooth less because 2DX is a smaller length. DX is your grid spacing again. And so you can support higher resolution topography. Or I should say you can support rougher topography at higher resolution. Another boundary condition is going to be your land surface types. So, if you look at ice sheet margins, do you want them to be blocky or do you want them to be fine grained like they are in reality? So you need to adjust your boundary conditions for that reason. Mountain glaciers are notoriously small kilometer scale features. And so if you start running at 7 kilometer, 3 kilometer, you want to make sure that those are represented. Okay. So part 2, we're going to talk about regridding. So it's an important tool for any student or scientist to have is to know how to regrid model output. This is especially true if you're working with an unstructured grid. And it's even more true when you're dealing with a grid that has regional refinement on it. This is a little overview on how you would go about regridding model output. And then I'll just sort of start by the difference between structured and unstructured grids. So we're all used to the latitude-longitude grid, in which, for example, the model will produce a surface pressure array that's a function of 2 horizontal dimensions, your latitude and your longitude. The index of those dimensions are monotonic and they're structured, so if you increase the latitude index, it's going to increase the latitude. If you increase the longitude index, you're going to increase the longitude. So you can anticipate what your neighbor is for the next index over because the coordinate is structured. Dot, 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 dot. It all makes sense. And we're very used to dealing with the latitude longitude coordinates. We derive the equations of motions in our dynamics class in this coordinate. We're used to plotting zonal mean metrics, in the zonal mean height, zonal mean precipitation, and that's inherently a latitude-longitude grid built into that metric because you're averaging over longitudes. And similarly, your stream function is based on latitude and longitude. You're taking derivatives in the y direction, which is your latitude, and the x direction, which is your longitude. So when you go to an unstructured grid, you just have one horizontal dimension, ncal. So it's just an index of a particular grid point. And so say you're at one of these grid points, say here, I know I can't seem to get it stuck on one, but say you're at one grid point and you increment that ncal dimension one more index. You have no idea where that new next grid point is. It could be right next to you, it could be on the other side of the globe. I mean, it's completely unstructured. So there's no information about your neighbors. And so you can't do a zonal mean because there's no longitude coordinate to average over. You can't do a stream function. There's no latitude or longitude to take your derivatives. And so it's much more useful to remap to a latitude-longitude grid in those situations so you can complete your analysis. I'll mention, though, that you don't always need to remap to that long grid to do analysis. Most plotting routines, like Python, can create map plots just from feeding in the unstructured array, the uncal array. So there's two methods. There's two methods to regrid. Maybe there's a third, but these are the two that I'm familiar with. So you can regrid entire netcdf history files. So It's you know, the CSM will produce unstructured model output, and those netcdf history files that you probably configured in your labs where you're setting your Finkel variables or whatever, those history files, you can remap the entire thing so that you have a new history file with latitude longitude coordinates. It's kind of quick and dirty, but it takes up a lot of storage space because you now have twice as many history files, your unstructured ones and your lat long ones. You can do this using command line packages like NCO and CDO. They usually require a mapping weights file as the input. And the mapping weights file contains sort of all of the weights required to do the remapping, such that you're basically just doing linear algebra of the unstructured data dotted with the weight file. And so this is how you would, if you have the weight file, it's as simple as just NC remap, path to weight file, your unstructured netcdf file, and then it'll produce an out.nc, which is the mapped version. The second method is regrading arrays on the fly in your analysis scripts as needed. This is more practical and sustainable. And what it means is, like, if you're in your analysis script and you want to plot zonal mean temperature versus height, you pull in the temperature array, which is dimensioned, time, level, and end cal. And then you simply will just regrid that array in your analysis package and plot that array. So most of these analysis packages have internal regrid routines that don't require a mapping weights file. These are not well documented, and they're not as accurate as using weight files generated from a particular software package. So if you do have a weight file, then the way that you would remap arrays on the fly is, here's an example for Python. So this is using the CESM library. I know some people don't like that library. There's an ESMFY library as well, which is, I think, that's the official ESMF Python library. And so you can probably do it that way as well. But this is how you do it in XESMF. You read in the weights with read weights, and you apply the weights, and your in data is the array you want to map. So then that leads to the question, how do we generate a mapping weights file? So first you want to find your target grid. 2 minutes?
It's to have some time for questions.
Okay, that's fine. So first you want to define your target grid. So what do you want to regrid to? It should be equal resolution or coarser. You don't necessarily want to remap to a finer scale grid because you're relying on the algorithm to make up scales that don't exist in the source data set. So if you're gonna do that, you should use a high order approach, and you should just not do it. That's my tip. Don't do it. So map to equal res or coarser. You then want to locate your source and destination grid files. And we keep all of the grids that are in CSM under HO, under the input dataset repo. And so I use script grid files. There's also ESMF mesh files as well. And we can generate mapping weight file using these two grid files and some command line software. So there's Tempest Remap, which is developed by Paul Ulrich at UC Davis. I use command line ESMF. ESMF is what we use in CSM to develop a lot of our mappings and data sets. And so how you would use ESMF is on Casper, you would load these two libraries, the ESMF library, do a module show. That'll give you the path to all the executables. And so the particular executable you want to use is this ESMF underscore regrid weight gen. So at the command line, this is all you do. ESMF regrid weight gen, -s to the source grid file, -d to the destination grid file, -m to the method, bilinear, conserve. There's a high order option as well, and -w, whatever you want to name this thing. So I'm sorry we didn't get to dessert. That's on me. But if we have time at the end, maybe I can give a couple applications.
We can, if you want, you can go.
How about just this one slide? So this is.
Yeah, you can go maybe to the end of, until the end of your spot, and they will ask question during the interruption to you in private. Then.
Okay.
Okay, let's do this. Then.
I'll just do this one slide, and I'll take any questions you have, because I threw a lot at you guys, I think. So this is the North Atlantic grid that I developed. And this study is led by Rob Will, so I'm not taking all credit. But what we're doing is we're looking at the response to storms passing over an SST anomaly. So this square is a patch of warm SSTs that's located over the Gulf Stream. And the snapshots are just of a storm passing through that warm patch at 1 degree on the bottom, 1/4 degree in the middle, and 1/8 degree on the top. The blue is precipitation, and this contour is the vertical velocity by the dichlor. So at 1 degree, your synoptic storms, your cold front and your warm front are kind of these single Gaussian features. And when you go to 1/4 degree, your front starts to be composed of different convective elements. And not so much in the warm front, but in the cold front, you're starting to. But as you can see, the size of these convective elements are still pretty large. So you only get a couple in there. It's not very realistic. So once you go to 1/8 degree, you start to populate your cold fronts with a decent amount of convective elements, and you're starting to form a realistic frontal structure. The yellow contours are the vertical velocities. And so it's showing you that actually the convective elements that make up the cold front and the warm front are actually transporting moisture and heat deeper into the atmosphere. And in the case of the warm front, it's not only transporting momentum and heat deep, but it's also transporting momentum and heat further poleward, upward and poleward. And so that ends up having an impact on the mean state. And you can get, if you run this experiment and you start looking at the seasonal response of sea level pressure, given on the right, you get an NAO-like response just to this SST anomaly from the ocean, where you have this deep Icelandic low, Azores high, and it's obviously much more diminished at 1 degree. And so these variable resolution experiments are opening the door to sort of understanding how the ocean forces variability in annual mode variability in the atmosphere. So I think there's a lot more to look at in these, this particular question about interannual variability forced by the ocean. So I'm going to stop there and take any questions that you might have.
Yeah, we have time for one question there.
Thanks for a great talk. I have questions about like vertical resolution things because you're mentioning about like a horizontal resolution over here, but is there any plan for the different vertical resolutions or like in CAM 7 or?
Yeah, so we don't have, this is only horizontal resolution refinement. No plans on doing vertical resolution refinement, but I will say that CAM 6, and I think what you guys are running are 32 vertical levels. CSM 3, which we're slated to release next year sometime, hopefully early next year, it's gonna have 58 vertical levels, 10 additional levels in the boundary layer, you know, and roughly another 10 spread throughout. And so you know, that is showing some improved structures of like boundary layer clouds. But that'll be available in the default 1 degree model as well. So a little tangential what you asked. We don't do refinement in the vertical, but we are now using an operationally higher resolution vertical grid in CSM 3.0.
Thank you.
Okay. Yes, it's 1 minute before the break. Let's come to talk to Adam here if you have more questions about this. Also the slide, because there were tons of information how to do this grid. Then it will be posted on the website later today. And also I'm here if you have any information on the previous talk. Then I have been asked, there are some breakfast, I don't know what's there, but there is no nuts at all. And then they ask that you start by taking one piece only. I didn't see the situation, but I guess there is limited number. Then don't take one piece, and after everybody goes, you can take another one. Okay, and then I recommend people coughing it through, that I notice people coughing, please wear a mask if you don't mind, that other people feel more comfortable. Thank you. Okay, then please sit down. Okay, we are starting. Yeah, sorry. Okay, then Jesse is going to introduce the last lab that's about diagnostic. Because we did this test yesterday, we are confident that it's going to work better than last year, but
Yeah, last year they got 2 hours of free time because the system went down. So yeah.
Yeah, then thank you, Jesse.
All right.
I'm going to get, you can start, but I will get.
Oh, okay. Well, hi all. Yep, and good job making it to Friday. I know it's been a long week. Hopefully it's been good. So yeah, this is the last lab of the tutorial, and it's basically trying to take all the numbers you all have been producing for the past 4 days and actually plotting them and doing analyses. And of course, what I'm going to show isn't the only way to do this. It's just the kind of workflows and tools we use here at NCAR. And of course, I spilled water on myself like 10 seconds before this talk started, but that's fine. Okay, so yeah, lab goals. The core language we use is Python. It's been a big shift. 5 years ago, a lot of folks didn't necessarily know Python. Now a lot more have, so maybe a lot of you are familiar with it. But of course, specifically, we're going to focus on Python and application to climate and geoscience. We're going to hopefully successfully run Jupyter Notebooks on Jupyter Hub, which I'll talk about if you're not familiar with. Obviously, the main goal is really to visualize CSM model output, the models you all have been running the past 4 days. And then finally, maybe learn about some of the diagnostic software developing here at NCAR. And there's a bunch of alphabet soup, which I'll go into. So real quick, if you're not used to Python, it's basically a scripting language. That second paragraph is like computer science speak for that. And then it's actually heavily used throughout at least CGD. In fact, the tools you've been running, like create new case, case build, et cetera, are actually all Python scripts if you were to open them. Of course, those are designed to use what's known as standard Python, which is just what you get when you install Python. For our diagnostics, we bring in a lot of third-party packages. And again, maybe many of you are familiar with them. These are things like NumPy, Xarray, Matplotlib, Cartopy, Dask, et cetera. And so again, hopefully we'll get a chance to use these in the lab today. This is going to be a little different than all the labs you've done before because we're going to be using, instead of opening a terminal, you will do that at the very beginning to clone the repo you need. But then we're going to go into a system called Jupyter Hub, which again, I think you all tried yesterday. And so what we're going to do is we're going to go on Jupyter Hub and then run what are known as Jupyter Notebooks, which is essentially just a way you can kind of embed Python code and plots within essentially what almost can kind of look like a journal article or a collection of text. And then there's also systems where which we won't use here, where you can bring multiple notebooks together into a single book. Clever naming. So yeah, you've all done this yesterday, but just to kind of go through it again. So you'll go to jupyterhub.hbc.ucar.edu. This is what it'll look like. You'll log in. I should have mentioned. You'll log in with your username and password. You can obviously just enter in your password and you'll get a duo push, but also on the tutorial materials, you'll see a method where you can enter your password, comma, and then a PIN code. Either one should be fine. So, thank you, Rory. Right? Yeah. So anyway, when you log in, you'll look at a page that looks like this. You'll just go ahead and hit start over on the right. Then this page will show up. It'll start off as Casper login. We want you to go to Casper PBS batch, which will be one of the options. This will show up, and the only 3 things you really need to change is in the queue. It'll probably start off with maybe I think just Casper main or something. So just change that to tutorial, and then make sure your project account is this UESM one, the one for the tutorial. Once that's set, go ahead and click Launch Server, and you'll get a page that looks like this. At this point, yeah, you can go ahead and start on the tutorial. And again, a similar set of instructions are on the actual tutorial website. And if you go to the diagnostic subsection, you'll see options for each component. So you can go ahead and once you clone this, you can start running those notebooks. And then you also see things for the more advanced features, which are optional. So yeah, I did want to talk a little bit about that alphabet soup before we get started. So there's kind of 4 packages that are at least discussed. One is Cupid. Cupid's very new, like literally less than 6 months old-ish. And it's mostly targeted for CSM3, but its design is essentially a push-button diagnostic. So you run your model, you just essentially run Cupid, and it'll generate a whole bunch of key metrics and diagnostics for your simulation. It also can do what's known as time series generation. So the climate model outputs what are known as time slice, so a bunch of variables, but at one time. A lot of times, though, we need time series, which is a single variable for all time. And so there is a practice example in the tutorial where you can do that time series conversion. And there's also one key metrics notebook, which may or may not work. So you'll let me know. Another tool you can try is UX array. Again, one of the big shifts with CSM3 is the atmosphere and land will be by default on what's known as an unstructured grid, so the spectral element dicore that I think was just discussed. That can be difficult to plot, right, because you don't have lat-lon information. And so Sizzle has helped, the computer lab here, has developed this new UX array library, which can allow you to essentially read in this unstructured grid directly and generate plots without having to do your own regridding or anything. And so again, there's an example of that you can try. And we'll hopefully use this a lot more with CSM3. One of the most popular diagnostic packages we have is the Climate Variability Diagnostics Package, or CVDP. This has been used extensively, well, pretty much for its name, to analyze climate variability, modes of variability, trends, etc. And what's also really helpful about it is it not only can work on a single run, but there's also a large ensemble version which you can use on large ensembles to generate, I guess statistics. I don't know what to say. Yeah, analyses on large ensembles that otherwise can actually be really difficult if you had to code it all yourself. And if you are curious, Adam Phillips here is the guy who basically built it all, so he can explain that much better than I just did. Cool. And then finally, the last alphabet in the alphabet soup is the ADF, or the AMWG Diagnostics Framework. Again, in the past, we had an AMWG Diagnostics package, which you would pass in your model run, and it would just generate a bunch of plots, mostly focused on the atmosphere. And this tended to be pretty popular, but it was written in an older language called NCL, which is no longer supported. So the ADF is an attempt to replace that with Python. So again, there's not quite a tutorial example specifically for this tutorial, but we do have an online tutorial for it, and so I've linked it there, and you can try it. And especially do want to emphasize this, it's mostly focused on the atmosphere, but it also is very soon getting a lot of new atmospheric chemistry analyses and high top models, so like Wacom analyses. So if that's also your area of interest, I would say it's worth checking out. Yeah, so I went through that. Oh, no, that was right on time. Okay. So that's it. Thank you.
For setting up the Jupyter Notebook, do we use tutorial today? Because it wasn't working yesterday. Setting the queue.
Oh, yeah.
Hopefully. It was working by like 4 p.m. yesterday, so hopefully it still works today. But if not, there'll, like in that same drop-down list, there will be an R number something 32. That will get you to the same place. But try tutorial first.
Yep.
Hey.
Hi.
Does the UX array package let you do anything besides make visualizations? Like, can you perform computations on it or regrid or anything?
Yeah, you can't perform computations on it. My understanding is I don't know if it actually will allow regridding to structured grids yet. it's kind of an open discussion of what's the tool to best to do regrading from unstructured to structured grids. But there's other things around. There's what's known as ESMF, which is a tool. There's also NCO, the NC remap, which can work. So yeah, if you feel free to talk to us if you have a specific example. But eventually, I mean, UX Ray is also under active development, so I could definitely see in the future it could provide regridding for us. So
Cool, thanks.
yeah, no problem.
Any more question?
Up at there. Yeah, yeah.
Thank you. For the climate variability part that you were showing, I was wondering if you can couple that to the land and like how, if like you can run experiments in some way where you can like just have initial conditions on land and then just use the climate variability to see how it changes over time.
Oh, well, yeah, you can do that from the model, but that package is just designed to help generate the analyses. So, you know, I'll pick on, so if you're familiar with something called the MJO, to actually analyze the MJO, you have to do a bunch of post-processing ahead of time. Like, you know, you have to like do 30 to 90 day bandpass filtering and then calculate the EOFs and then, you know, determine the, and so the advantage of the CVDP does all of that for you. So then you can just hit go and it just gives you the MJO result. But it doesn't actually modify, yeah, it doesn't like produce new file to then couple. Yeah, you'd have to do that externally.
Just a slight correction.
Oh,
it
sorry.
does a lot of things, but it doesn't do the MJ.
Okay. Dang it. All right, yeah.
So like the PDO or the NAO and stuff, it'll do that. But the MJO
I
requires
literally picked
daily.
the one oscillation.
Yeah, you
that
picked
it-
the
yeah,
one mode
like-
that it doesn't do.
Right.
Yeah, Adam is the developer of the CVDP. Then if you have question about this, you can ask him. Do we group them like yesterday in by component, or they just go wherever they want?
We can, but my hope, you know, most of the, I don't think it matters too much because generally the Python code that can work for one usually works for the others. I mean, you know, that's all. It's generally transferable. The one exception is the ocean because the ocean is on, you know, a tripolar grid, so it has a special pop tools call. But you know, I guess you can isolate the ocean people.
Yeah,
but
yeah,
otherwise,
yeah.
yeah.
Then yeah, there will be people of each component to help. We had two people helping for the land. There is Danny in the back. Danny, can you raise your Danny? Can you raise your hand? Then they can see. Then it's him. Then there was another person, Adriana, but she cannot be here today because she has a daycare issue. Then, but we will have Eric and Will that would be online if you need specific help with the land and if Danny cannot reply your question. Okay, then yeah, don't suffer alone. We will.
Cool.
Okay, then. Oh yeah, yeah.
I also wanted to point out, because we did that login test yesterday, so late in the day, we have like a 24-hour cookie timeout. So when you go to start Jupyter Lab, some of you might already be signed in and not get the login page, so don't panic, that's even better. Just launch a session.
Okay.
Thanks.
If one talk would disappear, then
Your explanation was great.
Okay.
It was like, not MJO.
Yeah.
Everything else.
this is Jim Edwards, who does a lot of the software engineering of CSM. And he's going to give a lecture on porting and validating CSM2. I know that people who run on derecho don't have to do porting, but it might be of interest for other people. We found sunglasses, if it's somebody's sunglasses. I will ask again. Okay, it's your floor. You have
All right.
20 minutes.
So, you know, many of you may want to port CSM2 to your college cluster or to a laptop, perhaps. And I'm going to give you some basics on how to do that. There's a couple of ways to do it. Let's start with that. You could define the new machine locally in your home .seam directory. So you would create that .seam directory and then put files that apply to your machine in there. That's what you want to do if you're going to be the only user, you're not sharing it with anyone else. But if you're going to share it with someone else, you'll want to define the new machine in your code sandbox. Wow, that's so you can share it with colleagues and potentially the CSM repository. So if you go into CSM, seam config, CSM machines, config machines, and look for a machine that closely matches what you're trying to port to, that's the easiest thing to do is copy that section into a new section, give it the name of whatever your machine is, and then edit as necessary. So if you want to do it in .seam, you would create a directory called .seam, and then copy or add files config machines, config batch, and config compilers.xml to that directory. And then the file config machines will have an entry similar to those found in config machines and so on for config batch and config compilers. And we'll look at those files in just a minute. And there's a minimal example in the source in this user-defined laptop template. And then, yeah, repeat this process with config compilers, config batch. Now, config machine is that's kind of the section that you'll copy to your .seam file. It's complete, right? It's everything that you'll need. But for config compilers, config batch, you're building on a more general definition. So there's a general definition of the flags you need for the GNU compiler, for example. And you'll just modify those to fit your machine. You might need an extra flag, or you might need to overwrite some of the flags that are already there. And the same with config batch. It'll have basic PBS and Slurm options, as well as, I think, LSF, and there's another one in there. Mostly people use PBS or Slurm. And there'll be a basic definition in there, and then you just need to add a few things like the name of the queues on your machine and how many nodes you're allowed to use at each queue. So yeah, defining a new machine in your sandbox, you do the same thing as above, except you're going to put it in the CSM source code. And then if you're really comfortable with it and you want to push it back, you can create a PR in our seam repository and ask for us to merge that in. And then what that gives you is when we do an update, you'll get that update on your machine. It'll just work because you've already ported it. So the 3 files of interest, I told you already: config machines, config batch, config compilers. And the config machines contains things like the path to the CSM input data, location of case directories and run and build directories. On our system, Duratio, we have a work file system that's persistent, and then a scratch file system that gets purged. So we put the case itself on the work file system and the build and run directories on the scratch file system, so that those you can save your case. It'll hang around for a long time, but the run will get purged after a while if you're using too much disk space. It also includes the names of the compilers, batch systems, and MPI libraries you can use. And for Duratio, I think we support 4 or 5 different compilers. You'll probably support 1 on your machine, maybe 2. The GNU and Intel compiler suites are both free now, so you can download those and install them, and they don't cost anything. So I encourage you to use the Intel compilers if your only other choice is GNU. GNU is nice, but it's a little slow. Let's see, and then the module environment. You guys have experienced the module environment this week in the tutorial. It allows you to have access to like multiple compilers, multiple MPI libraries, multiple chains of software, and load those into your path or unload them, so that you have a consistent environment. And you can download modules and install it on your laptop even if you'd like to. It's a useful tool. So the config batch contains definitions of queues used on your system, the submit arguments and batch arguments, and the config compilers. You might need link commands or compiler flags that are unique to your system. And then these are what the files look like. The text might be pretty small. But let's see if I can point at a few things. Where is, so dn locroot, that's where your input data is. I recommend if you're putting this on a shared system, make sure and put that in a place that all of your CESM users can read and write to. If you don't do that, then you end up with several copies of input data on your system, and it can take a few terabytes of disk space if you build too many cases. Let's see. So this particular machine, where's the pointer? Oh, there it is. This particular machine, they're supporting GNU and Cray compilers and MPitch and MPI serial libraries. This CPRNC is a tool that we use to compare netcdf files. So you can do, you can do a run of the model. It produces netcdf history files. You can save those to a baseline directory. Make a change that you want to try. Do another run of the model and compare those results and make sure you have the same results. If you don't get exactly the same results, then there's another test that I'm going to get to called the ensemble consistency test that will help you to compare those. Yeah. So and then this is an example over here, an example of what you need for a batch system. This one has a couple of queues defined, a normal queue and a debug queue, and you can see that for up to 16 nodes, it's going to use the debug queue, but after if you want more than 16 nodes, it'll go to the normal queue. And then the wall time, it'll set the wall time to this value. And then config compilers, you can append flags, or you could overwrite the whole C flags and put all your C flags in here. This is the names of the MPI libraries for various for a particular, in this case, MPI library. This is the MPI compiler. So this is for an Intel compiler, you have to set MPI I for it instead of MPI F90, something like that. And then the serial names of the compilers are here. And then this machine is using Trilinos, so there's a path to Trilinos on it. Okay, so now you've made an initial attempt at a port. You know, how do you test it? Well, the first thing you do is start with a simple case. Don't start. I see too many people do this. They want to start by running the experiment that that their professor or whatever gave them to do, and it's like a B1850 or something. Don't do that. Start small, do something really easy, and work your way up to that. It's going to be a lot easier, a lot less headache to do that. So start with something like an X case here. And then, a small resolution, give it your machine name. We called this case foo, so then you'd cd to the foo directory, run case setup, case build and case submit. You've already done that in the tutorial this week. If you run into a problem, figure out what the problem is, go back and do that step again. And almost certainly these commands aren't all going to work the first time. Refine your settings in the XML files, iterate on the above steps until all of them work without error. And if you have questions, try the CSM forum here. Oh yeah, and CSM 2.1 uses Python versions between 3.7 and 3.9, maybe 3.10 right now. Python is evolving, and newer machines will have newer versions of Python. If you get too new a version of Python, we may not have ported to it yet. So you can install like a Conda environment or a pip environment and an older version of Python to get everything working. And then once you've successfully built and submitted a case, build the CPRNC tool so you can compare netcdf files. And basically, I just told you to follow the instructions in the README. You need a few prerequisites. You need netcdf installed. I think that's it for CPRNC, but for CESM, you need netcdf. pnetcdf is a good tool to have. I think that's it. Yeah. And then after you've built CPRNC, put the executable in the directory specified by the CCSM, CPRNC variable and config machines, and then you'll be able to run the scripts regression tests. And that's another step that you're probably gonna run it several times. Run it, find the problem, fix it, run it again. And then once you're done with that, we'll go to the ensemble consistency test. Did anybody talk to you about this test yet? You recognize that graph? Yeah. So the ensemble consistency test, what it does is we have built on Cheyenne several years ago an ensemble of CSM 2.1 runs, and you can build like 3 instances and compare those instances in some 60 or 70 different variables to our ensemble. So in this graph, the ensemble might be the gray lines here, and your runs might be these red and blue lines. And probably this particular variable would not pass the ensemble test. So what you want is for your runs to be within the bounds of the ensemble or close to it, right? So this is a way to get around trying to make everything absolutely binary equivalent, which is really a difficult problem. So you do 3 runs on your machine of the ensemble consistency test, and then you can go to this website and upload the results of those runs, and it'll compare it to our ensemble. And it takes maybe 2 or 3 minutes, and it'll come back and tell you if you passed or failed. If you pass this test, you can be pretty confident that you have a good port, and you can have a lot of confidence in the science that you do with it. So how to get help? Post to the forum, ask a question in our Slack here. You can also open issues in GitHub, but you probably should do at least one of these two things first, and someone will respond and say, that's an issue. You should open an issue in GitHub. Don't go to GitHub first. Yeah, and I think that's it. Thanks.
Thank you so much. Do you have a question? Yeah, up there.
Thank you. I was wondering if you had any advice for like benchmarking and optimizing it for a machine, like changing should we be playing around with the number of tasks per node or the number of threads or yeah, what we can do
Yeah,
with that.
load balancing is a whole different topic. Okay. But there are, if you read about the test suite, the CESM test suite, there are tests specifically for load balancing in there, and talk about it more there.
Cool, thank you.
Question? Yeah.
Could you explain a little more why we need the ensemble test and not just like a simple, deterministic binary comparison?
So say you've changed, it doesn't take much to make the model give binarily different answers. So like just changing the order of math operations, doing the same equation, but doing b plus a instead of a plus b can change the answer, right? In the last decimal place or whatever. And then because it's a nonlinear system, that change in answer grows into a completely different result after a short time. Okay? And so by using an ensemble, you're making sure that your result kind of fits within what the expected result is.
So on a different computer, it might compile differently and do the math equations differently?
Absolutely, yeah.
Oh, okay.
On a different computer, you'll never expect to get exactly the same answer. Yeah, a different compiler, a different computer, a different number of tasks should not, but sometimes does. Yeah.
But on Derecho, you could do the same run twice and you should get the exact same answer? Yeah.
Yes.
Well, that answers my question, which was, is CESM deterministic?
It is.
It is. So there's no random processes.
There could be some stochastic processes in physics, but when we do tests like this, we turn those off. And usually there's a nameless control for something like that if it exists.
So it's not always fully deterministic, but we run it in a deterministic mode.
Yes.
Okay.
Thanks so much. I just want to know the number of examples that you need before you can say your simulation is
3.
3.
Yeah. And I understand for CESM 3, they're working on a new ensemble, and because the physics is much more complicated than CESM 2, we're not exactly sure it's going to be the same process as this one is.
Thank you. Please, this is a follow-up question to his question.
Yes.
So is the 3 the minimum number or the maximum number of ensembles you need to be able to perform a simulation?
So the 3 ensemble members is just to perform that test, right?
Mm-hmm. Is it the minimum number, or you can have more than 3?
You can have more than 3, sure.
So 3 is the minimum?
Yeah.
All right.
Okay.
Any more question? Otherwise, I will ask Jim, can you stick during the break? Sure. Just now, if people want to ask more question. Then we will have a break. I will ring the bell. When we come back, it will be the last bell. I think there is just a few snacks now. Maybe. Yeah, then, yeah, we will have a break and then come back at 2:10. I will ring the bell. Okay, then this is our last stretch. Then Dave came back from his trip, and he wants to welcome you now as official part of the CSM community. Then I will let Dave talk here.
Yeah, card-carrying members of the CSM community. Yeah. So hope everyone had a fun week. I'm hearing all the fun chatter, which is kind of implying that you probably made some new friends, which is a good part of this this event as well. And hopefully some of these relationships will keep going on in your career. And I hope you've got a chance to meet some scientists here at NCAR and got a chance to talk to them about your research projects and what you might do, and that you're starting to, like, the juices are flowing in your brain about how you could potentially use CSM in your research. This is obviously just the start, and as I mentioned in the beginning, it's going to be it's a long road towards using CSM for productive research, but there's a lot of exciting opportunities. So I just have a few things that sort of real brief summary here. Almost everything I think I'm going to say here you will have heard before, but it's sort of reinforcing some of the ways that Cecile called this CSM and you. So how you can become a part of a really integral part of what we do. And I think what you've been hearing this week, right, is we really do. We think about this as a community model, and we're doing it for the community, but we need with the community as well. If we don't have new people coming through, using the model in creative ways, and especially any of you who are interested in being model developers, there's never anywhere near enough model developers in the world. It's really a fun thing to do. We're hoping to find ways to get you involved going forward. So I just want to talk about, you've learned a lot of the basics here. There's always lots more to learn. I just want to talk about a few learning opportunities. So in addition to the CSM tutorial, there's quite a few component model tutorials that we run at a less regular basis, sort of as the scientists involved in a particular component get the energy and see the need in the community to do that. So keep your eyes out for that if you're really interested in learning more about the atmosphere or the ocean or the land. That's a good opportunity too. As you've probably learned, and a lot of the stuff here is cloud-based as well, but we support full tutorials at AGU, AMS, and we even did a tutorial at the WSCAP meeting last fall in Kigali, Rwanda. And I wanted to make sure to include this slide so I could make this joke. So this is really fun, and even I was like trying to help out and not hurt, but helping out with students. And yeah, we had like 40 students or something, 25 to 40 students there in Rwanda learning how to use CSM. And then a few of us went afterwards to go see the gorillas, which was a life rewarding experience. And this particular gorilla, I think he was confused. He didn't understand why the directory structure, it makes no sense. Like where everything goes in CSM, it's like, how could anyone possibly understand this? And even the gorilla couldn't understand. But please share your knowledge with your colleagues when you go back home. We try to design everything so they can be used by multiple people, and we really do feel, we hear about it, that the students who learn here bring it back to their lab, and then you get 3 or 4 or 5 students all potentially working together on things, and it's much more rewarding. Okay, this is what I sort of said at the beginning. It's still true. Earth system modeling is hard, but the CSM and Earth system models can be a tool in your research toolbox. And I don't know, I showed this quote that was in a meeting recently, and I thought it was funny. Earth trying to make projections in the future is obviously incredibly hard, and say, how do you know if they're right or not? And, unfortunately, observations of the future are not available at this time. So, which is always going to be true, but there are, as you probably learned a little bit today, there are ways to evaluate your models and understand what is good and what is not good about them. And that's another big step in your learning process, is trying to understand when, where, and how CSM can be appropriately used. And I think our role here at NCAR, we definitely feel it, and hopefully you felt it too, is to serve as a collaborative hub for the research community to help enable them to do the science that they want to do. And sometimes collaborate with them, but we don't always have to collaborate with them, but help, even it's just if it's helping you collaborate with each other. And now you have a network of people that you can, kind of draw on as your future collaborators. I know this question's always come up, and I think Cecile's already talked about it a little bit, but continuing to learn and potentially use Derecho is going to obviously be the easiest way for you to use CSM. Everything works on Derecho. because most of the time, because we try to ensure that it works. We're testing it all the time. You can port CSM to other machines, and I do encourage you to consider, if it's not already ported to a machine at your institution, to check, because often it's ported and you don't even know about it. So see if there's any other faculty or other larger systems that are running CSM. But if it's not, maybe make the suggestion to your professor or some people who are in lead to get it ported. But you can also try to run a Derecho, and your accounts are going to be active till August 31st. But when that access is gone, when the computing is gone, it won't be replenished. So you can't really do this for your own research. It's really just for continuing to learn. But there is an opportunity, especially for graduate students or students, to get allocations on Derecho. Small allocations are available for researchers at any US institution, at least, to get you started. It's probably not enough to do a giant research project, but it's allowed you to keep moving your ideas a little bit forward to then potentially apply for a bigger allocation. And especially those of you who have are supported by or have your professor or you have an NSF grant, you can apply for large allocations on Derecho. So getting involved more, we talked about this at the beginning, hopefully you've heard about it a few times, of the CSM working groups. And this is really the best way to get involved in smaller teams who are doing work that's maybe hopefully consistent or related to what you're working on. So I mentioned at the beginning, there's model development working groups and there's applications working groups. These have all different ways of interacting. There's email lists, which is one way that we interact with people. Many working groups have regular weekly or bi-weekly meetings, and people who are really keenly interested on staying really up to date with the latest and greatest will join in on those. And then we have our winter working group meetings where the working groups get together and discuss the details of the component model and interactions across maybe kind of related components. And then there's the summer workshop. And so those are some of the best ways. If you're interested at all, I recommend going to the webpage, and you can find the leads, either the co-chairs of the working group, many of whom gave talks here, or the liaisons of the working group. Learning and engagement opportunities. Obviously, there's the tutorial that we talked about here. Mentoring. So as I mentioned last time, NCAR staff are really interested and able to host graduate students or even do mentoring from afar and postdocs. And we do find that the students who come here and spend some time here, 2 to 3 months or even up to 6 months, tend to make a lot of really rapid progress because it's that day-to-day, week-to-week interaction that it's hard to replicate elsewhere. You can just walk down the hall and ask somebody your question. So I encourage you to look into that. There's, if your professor has money to do that, there's also programs that support graduate students here. Pretty competitive, unfortunately. And then there's the workshops. Our 30th annual CSM workshop is coming up this June, and we're trying to think of something special to do because it's 30 years. It's sort of remarkable we've been there. And there are a few people who have gone to every single one of those. I'm not one of them, but I've been to at least 20. There's an award for the best graduate student contribution to the CSM project, so something to keep in mind as you're moving along in your career. And that's a pretty prestigious award and highly sought after. So if you think you're doing some good work, don't be shy about telling your professor to submit a nomination for you or tell somebody here. So that's a cool thing. And then there's the winter working group meetings, which will be in February. And we don't have the dates. We're set them about now. So I'm meeting with Elizabeth next week to try to get those dates onto the calendar. But it should usually be in February. There's a CSM newsletter. Hopefully you heard about this, where you can get updates on CSM events. We point users to new or under-advertised features of CSM. You learned quite a bit about CSM, but the number of capabilities that CSM has is much broader than what you heard about today. And we've kind of realized it's hard to keep the community up to date. So we are sort of trying to roll out every newsletter, another thing, like maybe you didn't know that CSM does this, and then give a little bit of a spiel about it. Research highlights. So if you have a research highlight you'd like to get eyes, so this goes out to 3,000 people. That's a nice way to advertise your research. And there's quick links to a lot of commonly used pages. And one thing is our CGD YouTube page. Another thing you may or may not have heard about is we have a regular seminar series here at CGD, and most of that is about our system modeling. And so it's another great way to sort of keep up to date with the latest and greatest in our system modeling. So you can sign up for the newsletter at the CSM webpage. The Discuss CSM forum, as you get further into using the model, is really the go-to way to try to get your questions answered. Historically, scientists have often emailed the people they know at NCAR, and we have responded to them. But we're trying to get away from that because we realize that it doesn't benefit the greater community. So please try to use this. First, if you have a question and you're not sure, maybe there's an answer to it, there's a decent chance there's an answer here in the forum. And if you don't find anything, please submit something, and we do monitor this and respond to essentially almost every request that comes in that's a reasonable request for information. So this is really highly used. And just to give you an indication of how much it is used, this is a thing we're tracking how much it's used, and the total number of posts to the CSM forum thread is now exceeding 30,000 since we instituted this. So it's a pretty massive amount of threads. And even in any single year, we're getting about 1,000 different conversations. So a user will submit a request and we will respond to them. So this is not just like, oh, a few people are using this. This is pretty widely used. And as you know, usually when things get widely used, when they get more and more useful. And I actually encourage you as you kind of go through it, if you know the answer to something, go ahead and help, because actually this is more than we can manage. So we are seeing people not at NCAR helping answer these questions. That's really fun for us. And we're in the process of implementing, anyone who's tried to use this before, one thing that's a little bit frustrating is that a thread can go on, and it's hard to know necessarily what the best answer is. So people have kind of have an answer, and then someone will have another question, someone will say something slightly different. So we're going to try to implement a best answer flag in the forthcoming weeks here. Another way to interact and collaborate with us is through the GitHub. You sort of probably experienced using GitHub, definitely got experience to use it to download CSM. And each component model has GitHub pages. This is the CTSM one, the one I'm most familiar with. There's just a ton of information in there. It's a way to track what we're working on, what our priorities are. It's a way to track what issues are that we've already, bugs we've previously identified. It's a way to initialize some discussions, and especially if you are doing a model development activity, we really want you to interact as early as possible through the GitHub to let us know what you're thinking, put us into one of the categories. We have a science development or something like that. Please do that. But also, if you found a bug, don't be shy. If you think you found a bug, don't make a presumption that we found it already. We need to hear about it. And so the way we learn about bugs is often through these issues. That's one of the best ways to communicate that you found something wrong. So here it is. Yeah, if you found a bug, or if you think you found a bug, please file an issue. And we have no bugs, obviously. So it's going to be really hard to find a bug in CSM. But if you do happen to come across one, it's going to be a beautiful bug that doesn't do anything to you. But still, let's get it fixed, Ladybug. So that's it. Thanks for everyone for attending, and we really appreciate your participation here and hope you learned a lot. I'll take it.
Yes, thank you so much. Thank you so much. A quick question for Dave, otherwise we will go to our wrap-up session. No? People are tired. Okay, then. And wrap up. Okay, can you hear me? Yeah. Yeah, this is our picture of the CSM tutorial group. Unfortunately, when we wanted to do the picture, we had this setting at the time that the sun will be the right direction, and it was pouring rain. Then we did the picture inside, and it turned out kind of fun. There are a lot of pictures in the folder that Elizabeth have probably sent now. I didn't want to put the link here because everybody can go on the website and find the picture. We will do a selection of pictures we will put on the website. This one is a big dome with hundreds of pictures. Then to come back on the first day, I show you the goal of this tutorial. Then as a result of attending the CSM tutorial, we our goal was that attendee will gain a foundation of scientific understanding of the core CSM component and CSM feature. Then I hope we reach this goal. I believe we did, but you will tell us in the survey. That also, our second goal, it was during the lab that you are able to run and modify the model and use the output. Again, we hope we reach this goal. I think we did mostly. Then you had opportunity to network with peer and scientists. And I have seen you really talking to each other, and it's really enjoyable and talking to scientists. And I hope also we reach this one. Attain an understanding of high performance computing needed for CSM. Then again, we had people from CESL helping us. I don't know if I have myself a high understanding of the supercomputer, but I know who to ask. But I hope we reach this goal too. And also that we wanted really you to perceive the tutorial as an inclusive learning environment. And I hope we reach all this our goal. You will have a survey. I'm really a pain with this survey. But it really helps us to improve the tutorial in the future. Then you will receive the daily survey that you received the other day. Then every day I was getting less reply. And it's not too late to fill. And you will have also a wrap-up survey that's more general. The daily survey, it was really about each lecture to see, is it the right level and is it helpful to you? But then the wrap-up survey, you will have like room to make comment, and we will leave you a little bit of time here. It's in the agenda that you have time to finish it, because once you go home, we are afraid you will forget about it. Then, it's time to say goodbye and thank you, and it's always sad to have this group leaving, but I hope that you will come back at NCAR and you will become part of the CSM community, and I will run into you at workshop or CSM workshop or working group. Then Peter Jan at a little limerick, then I say, we have always this little competition between atmosphere and ocean people, then I say we should do one as atmosphere. Then I started to do, in the land of CSM where the coat does rain, the day starting early, yet we dare not complain. For who needs sleep when there is so much to learn, we are here to become CSM Pro intern. I thought maybe it's, but then I wanted to do better than the ocean. With eye wide open like caffeine-fueled night, we listen for hours to the lecture insights. No nap, no yarn, no just brain cell on fire. Who needs a break when climbing knowledge? Aspire. Then, the tutorial cue. Oh, a beast on its own. But with patience, we tame it, no groan, no moan. And last year, chaos, just a distant shame. This time, Jupiter fears and not the other way. Then the last, this one. In just 2 days with coding galore, we devour our weekly allocation and then beg for more. The ratio was smoking, our fingers were too. In the annal of CSM, our legend will accrue. Then, yeah, it's a little memory of CSM. Then, it's why when I was working on it, each time I was hiding when I was in the lab this morning. Okay, then, yeah, this is Elizabeth, come here. Then I want to thank you first for your patience because we had glitch. We have spent hundreds of hours preparing this. I have spent night, weekend, but I love it, and I will not complain. Elizabeth love it too. She spent night and weekend too. And then, but we are not alone. We have a big committee that helps us. Then this is all the people that contribute. We had the CSM tutorial committee. We had presenter. We had lab helper, and we had admin that help. Teresa is here on the slide too. Yeah. Then this is really a team effort. Then it's really, you see the number of people involved. It's not. I yet even do very small character. Then this is all I have. Oh yeah, question. And I know Frank, so you wanted to say something. Yeah, you can.
I just wanted to have take an opportunity to say thanks on behalf of everyone to all of those people, everyone at NCAR for making this just an incredible week. I know personally I've learned a huge amount and made incredible connections, but it's also just been really fun and enriching. And I think like you guys especially, but everyone has done an amazing job to create a really inclusive and like care-driven learning environment. And so we wanted to just like give you a small gift each to say thank you from all of us. And we've got some cards in there and a card for the whole teaching and admin staff as well. So a round of applause for Elizabeth and Cecile.
We should put the other people there. Oh,
I
thank
think
you.
you should maybe share them with your husband and your son for their artistic contributions.
Yeah, thank you.
And some chocolate. And Elizabeth.
Oh yeah.
And should I give this to you for on the rest of the helpers and admins?
Yeah.
So yeah, another round of applause.
Thank you so much. Yeah, thank you. Thank you. Yeah. Yeah, it's really kind. Yeah, we are touched. Yeah. I will not share with my husband and my son. No way. Yeah. Yeah, oh, true, I didn't put them. Too bad. Okay, then, yeah, now we have a little bit of time to fill our survey. Then, no, it's important to improve. Then if you have to leave to take the bus, you can go, or the shuttle, then can you? Yeah.
Yeah, thank you all. And I'm going to leave this for the admin team so to travel with it. But yeah, thank you all. It's also very kind. So Teresa and I are here to help. If you still have questions about the shuttle, we do need to speak to a few of you. I think there might have been some confusion because we got a note from the hotel that someone didn't check out, and we thought you were checking out. So that would be good if you might have that confusion, you can come see Teresa and I. So we do know a bunch of you are planning to go to the bus right now at the 3 o'clock shuttle. And Teresa and I and Hui also have our cars. So we do know that the baggage space on the shuttle will be crowded, but we will get you there. And if you're not heading right to the bus, the green ride shuttles will be out front at 3 o'clock if you're heading back to the hotels. And then if you have some other option that's not one of those two and you need some help, come see us. We're happy to help you find your way this afternoon. But thank you all. And so you do have the survey, both today's daily survey and the final survey in your email. So we do appreciate that. And today's message with the final survey also has some other links, including to sign up for any of our numerous CESM mailing lists. So you can go ahead and do that. Also to sign up for our CESM newsletter. I included that link. And then too, I know some of you were working with Eric yesterday and he was offering some additional land resources. So that's included at the very bottom after the footer on my email. And again, at any time you have questions, you can feel free to reach out and I'll point you in the right direction.
Yeah, thank you. Yeah, and if you need, I can drive also a few to the bus. Yeah. Yeah. And the sunglasses are still here. I don't know, maybe it's not our group, but. Yeah. Okay. Okay, thank you. Thank you to you. Yeah.